Live from the University of Texas at Austin, the Liberal Arts Development Studios present Essentials of AI for Life and Society. And now, here are your professors, Joydeep Biswas, Don Fissell, and Peter Stone.
Hi everybody, Peter Stone here. Welcome to class today. So we're now right in the middle of the segment on sort of applications of artificial intelligence. Last time we talked about computer vision. Next time is going to be on natural language processing, probably what a lot of you have been waiting for, and talking about generative AI models and things like ChatGPT. There are a bunch of readings to do for next time, but most of them are short, so don't be intimidated by it. But please, of course, do the readings ahead of time to prepare for the lecture. Today is on intelligent robotics, and robotics spans much bigger than artificial intelligence. It goes, includes things in mechanical engineering and aerospace and electrical engineering as well. But there's a lot of robotics that is very tied to artificial intelligence. And in some ways, you can think of artificial intelligence being an intelligent entity, but disembodied, not connected to the real world. And robotics can take that intelligence and put it on a body. And we have the good fortune today of having a lecture by one of the world's leading experts in especially humanoid robots and robotics in general, Professor Luis Sentis from the Aerospace Engineering Department. He got his PhD from Stanford in 2007, and he's here to tell us about an overview of the field of intelligent robotics. Take it away, Luis.
Well, thank you all. It's a pleasure to be here today. CS 109, what an incredible course, and being part of it is a great pleasure. I'll talk about the intelligent robotics as it has evolved over the years. I have to warn that there is a little bit of equations on my presentation, but by no means we are really going to go into trying to understand them. But at the same time, if we ignore them, it kind of doesn't give you the whole depth of what intelligent robotics is made of and what the topics do we use. Next slide. Oh, yeah, I'm the one person in the slides. Okay. So, so why do we need intelligent robotics? And it does have, obviously, pros and cons as any major technology. Some of us believe that robotics is it's going to become bigger and bigger in the United States, and it's going to be more used in outside of manufacturing and e-commerce into into our homes and community environments. Why are we pursuing these kind of systems? And rather than seeing them as systems that could potentially take our jobs and so on, which potentially can happen if we don't do it correctly, we can see them also as enabling technologies. In particular, small businesses, here students that are starting some sort of manufacturing and so on, and may not have the facilities to produce all of these kind of type of products, packaging, manufacturing and so on. So robotics really, I see them as an enabler as a multi-purpose sort of general versatile machine that can help for this kind of opportunities. Besides that, going back a few years ago, the National Intelligence Council publishes periodically reports on whether it's going to be technologies in the next 10, 25 years are going to make it big. There was a report back in about 15 years ago, anticipating what was going to be big in 2025. And we see things like biogerontotechnology, which is the use of technology for increasing the quality of the elderly, maybe even extending human life for everyone. In energy, biofuels, clean coal technologies, we've seen definitely some of these happening. And finally, service robotics. By 2025, there was anticipated 15 years ago that service robotics will be big, and then this is really happening today or about to happen. And for some of the reasons I have mentioned before, and I'll continue mentioning of why I believe service robotics is important for our societies. Maybe one of the important reasons is what happens as we age. So here's a table by Factronic. Is a European company. Europe has maybe an elderly population. It has also a decreasing pyramid of in birth rates. And what was really striking to me is that we lose mobility very rapidly. And at 70 years old, 20% of the population lose mobility, and by 80, we have 42% of the population now expecting to live, beyond 90 and 100 perhaps by the end of the century. We're going to have really hundreds of millions of people across the world that they really have problems with mobility. And that's one of the places that I see robotics having great help, especially having had parents-in-law living abroad that they really needed a lot of attention, and it required ourselves to travel back and forth. So robotics could allow to have even better quality of life for this occasion. So I like to see all the positive ways in which service robotics can help, and of course try to be very sensitive about labor markets, about the use of robotics for violent activities and so on, which are not in the places where I like them to be, and then focus on what is positive for our societies. I also want to introduce my lab, and my lab is called the Human-Centered Robotics Laboratory, and it engages in precisely these sort of questions, how these complex embodiments, by mimicking some of the capabilities of humans in the form of humanoids in particular, they can help us in all of these things, elderly care, mobility, allowing small and medium businesses to accomplish tasks that otherwise they require more personnel that cannot be afforded by these people, but also other type of embodiments, transportation systems, personal transportation systems in healthcare. We have a strong focus on community robotics. Does it make sense? Many of us here at UT are working with robots that can deliver services. They deliver tours. They deliver objects. They monitor the state of the buildings and so on and so forth. Is that something that the community wants? That's precisely that study. Exoskeletons could be important for those of us who lose mobility at a certain age. And there's basic kind of dynamics and controls studies that allows our students in engineering and computer science to become just more knowledgeable of what it takes to control these robots. And finally, human factors down at the bottom. It's becoming increasingly more important. We team up with others developing sensors for brain activity, for stress activity, and so on, because we want to make sure that if there are robots around in our communities, they're blend in the right way with us, and we really want them to be there. Something great that is happening at UT is there's a lot of activity and many companies emerging, and a lot of the robotics and AI faculty have companies, and thanks to UT, this is really encouraged. This is one of them. I've been involved, and they make these sort of really sophisticated humanoids that it is to be seen if there is a demand to do something useful. And for the moment, it's an open question, and a very fashionable open question this year with Tesla and multiple companies in the US and other countries developing this sort of complex machines. So please do write me if you want to come to see them at a certain point. But one of the things I want to focus today is in a dichotomy, or could be also blending them together, which is model-based robotics and machine learning robotics. I wanted to make a distinction between the two. So I put this slide today. And what we see on the upper right side is a model-based approach to robotics in which we build some sort of mechanism. This is an actuator in this case. And we know all of the information about the mechanism. We know the kinematics of this system. We know the inertia properties, the gear properties. If there is any elastic element inside, we also have it very well characterized. And that allows us to kind of put together what we call the equations of motion, or the inverse kinematics or forward kinematic equations. And that will work for decision making or for building better robots, whatever it is, right? That is in contrast to what we see down here, is a handmade sort of figure I made today, where it shows the basic machine learning loop for supervised learning, in which we have a forward pass, and there are several layers. We have data input, we have a linear process, we have an activation function, we have a cost function, and we will have the famous backpropagation that allows you eventually to compute the cost gradient, and then through something called Newton optimization, then you can learn to mimic the data that you have collected before. So one is data-driven, really, and the other one is model-based. And I'll talk about robotics from these 2 points of view today, if you will. Okay? So let's start with the wealth of model-based methods that have dominated robotics for many, many years. And that my lab, it turns out, has been involved in. And the first one is precisely these actuation systems. These type of actuation systems. Here you see the same drawing we saw before, but now this is really the encasing and embodiment of this actuator. This is taken as a model-based mechanism that's incorporated to the control loop, is deploying this kind of humanoid robots like this NASA Valkyrie humanoid robot. And we use other model-based approaches for these robots to do this task. This is highly teleoperated. And there's a lot of cool things that can be accomplished with these model-based approaches. In particular, the control loop, you don't have to really go into the equation, but in order to control these highly articulated dexterous systems, they have arms and legs and center of mass, and a head has to look into places. They might have multiple contacts and so on and so forth. This has to be formulated into a big problem. So this, we call them optimization problems. And then here, the only thing to see in this equation is that every single of these parameters, EI, AI, J, and so on, are models, are similar to the models we saw for the actuator. They're based on kinematics and dynamic properties. They are not learned through some machine learning approach. And those have worked very well for the behaviors that we just saw before. Obviously, for deploying these behaviors, we need to couple these with software, which can be also model-based software. In the case of model-based software, it will likely run on the CPU, right, on the GPU. And here we see yet another architecture. These algorithms, these optimization algorithms we see down below are very similar to what we just saw before. Each of these matrices and vectors is well known a priori, and they have allowed to do quite a bit of versatile behaviors. One of the complicated problems of these model-based approaches is models come from sort of offline understanding of the physical world. So when you actually deploy them in real systems, they tend to misbehave. This is in the area what we call robustness of deploying these systems. So there is a lot of recursion and reiteration of these model-based algorithms in order to achieve wonderful tasks. I'm going to go directly into walking. For instance, walking theory in the theory and the deployment tends to be largely distant, if you will. There's a large gap. And I'll talk for a second on how do we cover this gap with model-based approaches. But let me first talk to you about how do we also use model-based approaches for walking, okay? And then for the last century or so, walking has been modeled with what we call an inverted pendulum. This means a pendulum that we reverse. The big mass is on top, and that kind of models the center of mass of a human body. And then the endpoint of the inverted pendulum is on the feet. And that, once we remove the human, it becomes just this very simple mechanical and dynamical system, which the equations are well known. They are nonlinear, but they can be linearized easily. And then with this simple model, great things have accomplished, including a lot of the videos you guys have enjoyed from Boston Dynamics and other companies. What you see on the right side is the trajectories can be predicted for walking on something called the state space of this system. So once you have these models, now you can take decisions on when to switch a contact, when to apply contact with the hands, and so on. And just using these simple inverted pendulum models, you can explain and you can control behaviors like walking on rough terrains or doing some of these wonderful Olympic feats with these very simple models, okay? Going back to where we were before here is more kind of the nitty-gritty of what really happens underneath when the model up there, if you know Simulink and MATLAB, is exactly that kind of model-based approach for walking. I'm not going to go into these equations, but when you deploy them in real systems, there is a lot of uncertainty. The place where you thought you were going to put the foot, you're going to place your foot hold, it doesn't happen. There is uncertainty on the state estimation of where you think your body is, the velocities, and so on. So this can still be analyzed with kind of classical control approaches, and a lot can be done, but there is certain limitations to all of these body of work of locomotion. Now, another thing I want to bring up is that to reduce the gap between the models and the deployment, we need to build better hardware. That's often done iteratively, right? So building robots that are okay from day one is difficult. Fortunately, we have the opportunity of improving structures, controllers, and sensing, and so on and so forth. But if you do all of these, then you accomplish behaviors like these ones. These are model-based approaches, with these kind of tiny feed robots, we call line feed robots, accomplishing these incredible dynamical behaviors and with quite a bit of robustness, okay? Just wanted to bring you this awareness to what we're capable of doing with model-based. Other places where we see model-based making a strong impact is on industrial robotics, especially now that the US is doing terrific with e-commerce, with providing truck loading and logistics for like FedEx and UPS. This is a company we collaborate with, Dexterity. And in particular, what you see on the right side is the use of similar optimization algorithms, model-based, where we take into account certain types of behaviors, vibrations, and so on, also model-based, and that improves tremendously the efficiency, the speed, and so on of these systems. Another example of model-based. The final model-based I wanted to show is on exoskeletons. Exoskeletons haven't made quite the impact that we expected in the communities, but they use also control algorithms such as those ones. They look really similar to what we saw before. Everything here is models of transformations of coordinates, the models of the gravitational effects, models of the forces, and so on and so forth. It's still model-based. We also utilize models of the human muscle. And in particular, we try to learn the kind of the non-trivial, non-linear dynamics of the human muscle, because once you are attached to an exoskeleton, you are a coupled system, a human-machine system, and you need to have certain model of the human. And for these intelligent behaviors, once you have the two of them, you can apply, again, model-based signal processing algorithms, and then you can accomplish these very cool behaviors of what we call strength augmentation, or people have kind of weak muscles, being able to regain walking, and things that we believe are going to be important down the line with the pyramids of population that we're seeing today. So let's put aside all of this wealth of models that we've seen. Let's start an intro to the use of some learning approaches. And in particular, learning has been very useful for approximating the dynamics of these systems. And a lot of the computations that you see in these optimization methods are really lengthy. So machine learning offers us the possibility of computing at very fast, approximating those systems, computing very fast these behaviors. For instance, let's say that you want to accomplish walking into these environments. For that, you need to have what is called the elevation map. You need to know all of the obstacles and things that are in the environment. And now, let's say that you still want to use model-based algorithms producing these behaviors. Every time that you consider a foothold as a candidate, you need to compute all of the kinematics of the robot, which is a very expensive computation as a model-based. So what we can do is approximate it with a neural network. We have here on the left side, similar to the inverted pendulum model that we saw, we call it centroidal momentum. The inertia, a dynamic property of these robots, is very expensive to calculate, but we can approximate it using supervised learning in order to approximate it with a neural network, and now we can compute it really fast. So when we run these very expensive model-based optimization problems, we can incorporate a few computations that are data-driven, and that speeds up an approximation, data-driven approximations, that speeds up tremendously the the capabilities of these optimization algorithms. Other places where we see combination of model-based and model-free is on this kind of search behavior. This is more recent work. On the lower right side, there is a robot at the end that is searching for this suitcase on the front left. And is using sort of something called information gain, which is a model-based approach, but it doesn't know anything about the map. So it could try to identify walls by using geometry, model-based geometry. But in this case, we use a classifier, a learning method, in order to distinguish what are walls from what are furniture, what are objects, temporary objects, dynamic objects. And that allows us to speed up a lot of the search and finding what is interesting to ultimately search. So you can see the robot going everywhere, and ultimately it finds the suitcase. Okay, so those are hybrid model-based, ML-based, learning-based algorithms. Let's go for the last part of this sequence of transitioning from data-driven to learning. Learning can be used for either approximating dynamical systems, rigid body systems, also soft systems. We see more and more robotic systems, for instance, hands, that they mimic the human hand. They have soft parts of it, and those don't obey quite of the kind of Newtonian laws. So we have to find ways to approximate those, and machine learning approaches like Gaussian processes or deep learning approaches can help with that. We saw also the combination of both of them with model-based approaches, but so far we have seen only decision making, like for walking or for these kind of NASA behaviors with the Valkyrie robot, only using optimization algorithms. The question we're asking here is that can we replace the model-based optimizers as decision makers? Can we replace them entirely with deep learning algorithms or other constructs, okay, in robotics to make robots more versatile? And then this is perhaps driven by the fact that a lot of the classical control and modeling approaches, they have been based on what we call a state space, and the state space is really small. It has maybe 30, 40, 50 degrees of freedom and corresponds to the kinematics of the robot, the joints of the robot is what we call proprioceptive states, the internal states. But as when we consider external states, vision, tactile, radar, now we're seeing, for instance, pin-sized radars that you can put on the fingertips of a hand. And so we see now multiplicity of radars, touch sensors, and then the cameras, even multiple cameras on a robot, right? Now you have millions of features, millions of inputs that you're putting to a decision maker. And it turns out that model-based approaches, they break down. They cannot take 5 million inputs, right? So we need to have a dimensional reduction, something that does interpretation, does decision making, reduces the dimensionality, and now you can send them to some model-based approaches that they work with very small state spaces. So recently, with other faculty like Professor Yuki Zhu from RPL and my lab is expert on model-based algorithms. Yuki is expert on sorry about that, is like sometimes transition automatically. We've explored precisely a combination on an ideal fashion of the two of them in the form of imitation learning. And imitation learning is coming out as a very important paradigm for what I call telling robots what to do. In the sense that, imagine the hypothetical scenario that you receive a humanoid robot of the future to your home. Let's say it's inexpensive and it works well, it doesn't fall, it's robust and so on. Now, it might have some pre-trained models of how to take your plates and put them in the cupboards and so on, but you're gonna have a bunch of other things at home that the robot is not aware of. So you have to customize the training, and the best way to do it is through imitation learning. And imitation learning, for instance, you can put yourself a VR headset with controllers, and then you can even show it in simulation, perhaps. You have a simulation of the robot. You teach it how to manipulate that particular object that is not in a pre-trained model. And now you maybe train it, teach it a bunch of times, and then the robot now learns how to do it, has it in this database of models, okay? And so on and so forth. This is coming as a very powerful paradigm for telling robots what to do, and it's the flavor that we're using between these two labs. Now, it has a long history, imitation learning. Not quite in the humanoids, maybe community has appeared more recently, but we've seen a lot on kind of bimanual manipulation in the motion capture, through motion capture of the whole body, and then retargeting for computer graphics, and so on and so forth. But we've seen it less on humanoids, which suffer from many other things, in particular what we call floating dynamics. There is management of collisions. There is management of several physical effects that are important. Maybe also collisions become very important, and those have to be taken into account as well. And it's difficult to kind of incorporate all these criteria. So here we recently got this paper accepted in Humanoids Conference on what we see on the left side is a deep learning imitation approach in which we have this high dimensional future input of cameras, joint states, robot poses, state machines associated with kind of the low-level controllers. And then on the right side in the middle, we have a variety of machine learning approximations, in particular things like Gaussian processes, which are statistical regressive processes for approximating trajectories. And we have also what we call logistic processes, which is kind of on-off, open the gripper, close the gripper, or multi-level logistic regression, which tells you which type of walk do you want to choose, walk forward, backward, to the side, rotate, and so on. So those are kind of very classical representations of ways to take decisions. We can learn that, all of these triggering functions and approximation of the trajectories, and now they have to be orchestrated by some other process because we have a sequence of them. We're not just learning to move the hand and pick up something. We're learning how to do a whole processing of a task. Maybe, having the marmalade, taking it and removing the lid to the jar. This is not one trajectory, it's a sequence of trajectories. So this RNN, this recursive neural network process, learns how to trigger all of these trajectories, right? That's where deep learning and imitation learning, through imitation, we can train all this policy. And then now on the middle side, we have these fewer states. We're only having open and close, moving the hand trajectories, and then how to walk, which now can be sent to a model-based algorithm similar to the ones we've seen before. And that gives kind of these incredible nice behaviors. Now, this is what we do first. First, we try to have fun. And in this case, we have one of our humanoids, Draco 3, purely teleoperated. And it shows you that by teleoperation, which is the means by which we accomplish imitation learning, these robots can do quite a bit of things, right? They can, do a whole meal of ramen, which turns out that my students love to do it. Can this construct that we have do the entire thing on its own? And not only can it do it on its own, but you have variability over these objects. Maybe the pot is bigger, and there is more ramen, the box is different, and everything is different, and it kind of is robust to all of this. Those are the questions and the promises that we have soon for these type of operations. I'm not going to go through the whole video, but they ended up eating the ramen, I can promise you. Now, what is under the hood is for more practical tasks. Is here, for instance, the disassembly of a cap, of a can. We have a teleoperator, somebody at home perhaps that wants to teach that for that particular can, and he does it over and over. And one of the key questions here is, well, how many times we have to do this? It turns out that currently for our method, we have to do it 250 times, right? That's, I want to say, unreasonable that a robot comes home and you have to spend 250 times to teach it how to pick up, your broom, okay? So hopefully in the future, we only have to do it like a couple of times, and then it kind of leverages these few shots for generalizing. So here's the outcome. Maybe the right side is a little more interesting. There's a dual arm behavior, and it has indeed learned autonomously to perform this sequence of tasks, to trigger them. There is nothing rule-based here. It has learned when to open and close, and it does it over and over with certain level of variability in that we place the can in different places, and and it does it, right? And ideally we want to have these for different cans, sizes, completely different places, postures of the robot, and so on. It's coming really, really soon. I'm gonna and here we can do similar things in simulation for now that involves at the same time walking behaviors. This is now in progress. We'll have it soon in the real robots. If I may, do I have still some time? Yeah. So maybe 5 minutes? Okay, great. So as you may know, we have this wonderful organization on campus called Good Systems that it brings together a variety of people from everywhere, from humanities, from the schools of public affairs, from the engineerings and the computer science and so on. And that allows a wider conversation of why intelligent robots are needed or are not needed if we discover they are not, right? And so here, just a few of the people and the diversity of backgrounds, if you know some of these folks. But one of the projects that we are investigating is what we call Living with Robots. It's supported by multiple sources of funding. A fellowship from NSF. We have something called a Growing Convergence Research grant as well. And we are deploying robots on campus. Those robots are, quadrupeds, spots. You might have seen them on campus. They are delivering services such as tours, such as inspection of buildings in particular. So they're just looking around and saying everything is okay. And then in the future, they might deliver, escorting services. We've conducted interviews that some students are worried at night, and they want a robot connected to a phone line to be following them, if you will, and delivering objects and so on and so forth. But what is important is to understand if people on campus feel comfortable with these robots and what other things they might expect from these systems. Aside from doing their business, they might expect that the robots can be stopped and you can ask questions. Please indicate where is this and such building, or hey, there is a bunch of people down the street. What's going on? The robot might answer, oh, there is a celebration for the baseball game, whatever it is, right? So there's some other social services. We're trying to discover how can these robots be useful for our society. But one of the things that this leads to is that these robots, in the autonomous world, in the intelligent robotics world, they need to be able to understand how people are moving and then avoid collision at all costs. And that can be done in many ways, but we can leverage similar techniques that we saw before in terms of imitation learning. So here, also work with UK and my lab. We see on the top side, it went really, really quickly. We saw an imitation learning algorithm similar to what we saw before. And there's a reinforcement learning process that learns to turn very quickly. Because as you can see here on the right side, the robot is avoiding this very narrow environment, this everything. It's avoiding every pixel. It's not sort of putting a bounding box on the human and avoiding the entire human. It's taking all the pixels and is constructing a policy where it decides to turn left and right based on every single pixel that it's seeing. And for that, we need large data sets. This architecture that we showed before, I'm going to just skip it, where literally we have students driving cars for many, many hours, over many days, over many different environments, with people, without people, narrow, wide environments, and so on. And those data sets allows this supervised learning approach in order to learn to not collide and avoid these people around. This is a study by my lab. There is in UK. It turns out that other people involved in this Good Systems project are studying the same thing being done outdoors, and that's going to allow better safety for our robots. The last slide I think I have is that none of this can be done without either asking people if they want to have intelligent robots around, or measuring things that we believe are indicators of whether people like things or not. So certainly we're conducting questionnaires, but also we are putting sensors. In here on the second picture, we see what we call electrodermal sensors. These, they measure the opening of the sweat glands. It turns out that they open in milliseconds, although sweating takes time. But if a person is stressed with sensors right away through sweat glands. So that gives us ideas of when the robots are around, if people kind of get stressed from a physiological standpoint, of course we have to complement it with questionnaires. And it's precisely this study with good systems that is going to allow us to say our communities like these things or don't like them, and it's going to drive the future involvement of robotics in our communities. That's pretty much all. Just if you are into robotics, there's going to be a conference in December here called Humanoid Robotics. We're going to have a bunch of humanoid robots over here. Come and see them in the ER building, December 12th to 14th. Thank you.
questions in the chat, and I'll try to keep monitoring it in case there are more. The first thing, just to advertise quickly, if you are interested in robots, Luis and I and the rest of the faculty on Texas Robotics are going to have a robot parade outside of Gregory Gym a week from tomorrow on October 12th. Thursday around noon. And so all of the robots from our labs are going to be out there, and a lot of the faculty and students will be there for you to ask questions about. So some questions. So first one I'll ask is why, Luis, why does it take, why do you have to teach a robot to do the same thing 250 times?
Right, so there are two reasons for that. And I want to put as the first reason variability. As you place objects and in an environment, what you don't want to do is have the robot teach a single trajectory that it drives you to that particular object in that particular position for that particular configuration of the robot. So every time that you place the setup and you repeat it, you add variability and hopefully, as large as possible, right? So ideally, you will be placing, your can everywhere on the table, and your robot, you will be placing it, farther from the table, closer to the table, turning, and so on and so forth. And that data set, it will become a much better representation of the variability of the real system. So now your trained policy, your trained model, when deployed, it would allow you to cover all of these more realistic situations. And the second is that the nature of supervised learning, it does benefit by having large data sets. So having just one set of trajectories is not going to allow to do optimization and learn the model as good as if you have larger data sets. But of course, all of these is in flux, and methods that maybe some things can be simulated after giving a single demonstration. Are being developed. We're going to see a decrease in the number of demonstrations in the future. Yeah, thanks.
Great. We have a question from the studio audience.
Yes, please.
So, how will these human-centered robots become more cost-efficient both economically and environmentally?
Okay, the first question I think I can answer well. So how they become more economic from a manufacturing point of view, and then environmentally, we are investigating as a whole world community very heavily this problem, and the economies of scale have kicked in robotics very recently. You can buy T-motors, what is called today, for a fraction of the price of motors 10 years ago, like 10 times cheaper. Gears might no longer be needed and be replaced by direct drive or even 3D printed harmonic drives or gears or pulleys that are much cheaper. Controllers themselves and the electronics, amplifiers, the power systems are becoming much cheaper. So we're seeing definitely a cost per degree of movement that has decreased by a factor of 5, if not 10, in the last few years. The last thing that remains is the structure itself, and we are going a little bit slower on that front in that transmissions, you might have the motors placed somewhere in the robot, but then the part that moves is farther away. So just like a bicycle and the brakes, right? So you need some sort of cables, hydraulic systems, or some mechanical bar mechanisms. Those tend to be very expensive. There is new methods and simplifications and clever mechanisms that allow a significant reduction. Okay, so we definitely are going to see robots, humanoids for I believe that some of the Chinese are being sold for $90,000, a full, what we call adult-sized humanoid. That's today. Probably we're going to see a price of a car pretty soon on a useful humanoid robot. Environmentally, is a little bit hard to compute the cost, but I would say the power usage is important. So if you have a robot that uses 200 watts as opposed to 1 or 2 kilowatts, and you end up having many, especially in the logistics industries, in the FedExes and UPSs, they're going to have many of them. That plays a very, very important role. And aside from clever mechanical designs and better actuators that are more energy efficient. Just with software, you can do significant improvements to be much more power efficient by a factor of 40%, for instance, by just incorporating notions of the feedback process, of the vibrations, and so on and so forth, or receding horizon strategies that allow you to save a lot of power. Just going to say these things. Now, in terms of the fabrication of 3D printing or batteries or so on that have an impact in the environment, I'm not fully familiar with, and I should be, and I appreciate your question. Next time, I'll definitely look into the impact of all of these constructions.
Good. Here we have a question about just a straightforward one about terminology. So you've been using the word feed forward. Can you explain what you mean by feed forward?
Yeah. So feed forward in everything, in controls and in machine learning, is the process by which you have a function and you just apply this function as a dependency of a previous state. And that function is going to affect a subsequent state and so on and so forth. Okay, so it's a sequential computation, and it's feed forward because it goes just in one side, right? So it doesn't require feedback. So it doesn't need to compute the end of the result and then bring it back to the input and recompute. That would be as opposed to feedback mechanism. So feed forward doesn't require the feedback loop. In machine learning, there's a feed forward path and there is a back propagation path that goes backwards. So these are the two interpretations of feed forward that I can give today.
So one student asked, how long does a robot's power tend to last? Do robots know when they need to be recharged?
Good question. So is in flux. Again, we just submitted a paper to ICRA, is a large conference, happens every year, through software, being able to increase 50% of efficiency of robots with the same sort of battery system. It's in flux as well because right now we're using lithium-ion batteries and so on, but fuel cells sooner or later are going to come a reality, and then we might have other type of we can have combustion engines as well, and other more dense power delivery systems. But I think that the common sense is that for these complex mechanisms, we ought to aim for 4 hours of operation without recharge, whether it's a robot on wheels moving around, or a dog robot moving around, or even an entire humanoid. This is what the consensus in companies I'm familiar with we're aiming to. There was a second question for that, or
no? That's it. So, but a different question. So, a lot of, and this one just came in. A lot of robots seem to move with wheels. A lot of move in ways that seem to mimic biology with 2 or 4 legs. Why would you? Is there research? First of all, into robots that move in completely different ways, and why would you, you focus especially on leg locomotion? Why is that a focus for you? So the first one, is there research into robots that move in different ways?
Well, absolutely. There is tensegrity robots that are a favorite of some of the space agencies, and those are sort of parallel mechanism systems with multiple limbs, like a ball, where there are pneumatic actuation. And they have, they have a lot of versatility and power efficiency that in unconstrained environments, in planetary setups, Mars and Moon and so on, could have great impact. In particular, in Earth environments, and I'm going to say also space environments, but in particular in the space habitats. And I'm saying that because as a Department of Aerospace Engineering, we do have projects with NASA and so on. And so I want to start with that, perhaps, as a niche application, which is space. As you may know, Johnson Space Center does a lot of human space flight. The US wants to set up habitats in the moon and beyond. We're not going to have 5,000 square feet houses in the moon right away. We're going to have probably very humble spaces, right? And robots, we believe, are going to go first. They're going to set up, they're going to just try the facility for humans, right? So I don't think we're going to have the luxury of having a rover or large wheels around, and of course, plus all the steps and to go down and go up and so on and so forth. So yeah, that's the answer.
Good. So thanks. Thank everybody for your attention, and look forward to seeing you next week for the applications on natural language processing.
Thank you.